All right, I wanted to go over the rules that we have for using our logical symbols in derivations or proofs. And so I'm just going to go over this document here. Basically, the idea is that for each of our four connectives, not, and, or, and the arrow, there are two rules. One for introducing the symbol into a sentence, and one for eliminating it from sentences. Okay, so we'll start with the not rules here. So you can see we have an elimination rule and an introduction rule, and these are very similar. Okay, and so the idea here is if we have made an assumption of not P, notice the horizontal line here meaning that we've made an assumption, and the assumption that not P leads to this kind of intolerable pair of conclusions, namely a contradiction, some sentence Q and its very negation not Q, well then because it's not P that's led to that calamity, we are entitled to the conclusion that P. Okay. And similarly for the introduction rule, if in fact it's the assumption that P that leads to this calamitous result of Q and not Q, then we can conclude that it must in fact be not P that's true, since the idea that P is true leads to this impossibility. Okay. Here are our rules for and. You'll notice that we have, in this document and elsewhere, you'll see two different symbols for and. So there's an ampersand, but there's also this little wedge shape here. Okay, both of those mean and. The elimination rule for and is pretty simple. We have some sentence that contains an and, P and Q, and the idea is that, well, if that conjunction is true, then of course each of those two conjuncts must itself be true. Right? So that is, from a sentence like P and Q, we can infer that P is true. Or, similarly, we can infer that Q is true. Okay. And the introduction rule is also pretty straightforward. We're not going to be able to conclude that P and Q is true unless we know that both of those conjuncts are true. So if we have P and we have Q on prior lines, then we can conclude that the sentence P and Q is also true. Or is a little bit more complicated. The elimination rule, if you just think about this in the abstract, it seems like the elimination rule should be abstract. Should be complicated. Because if our sentence is P or Q, well, it's hardly clear what one might be able to infer from that. Okay? But here's the idea. Suppose that we have the sentence P or Q, and in addition we have subproofs, one for each of the disjuncts, and each of those subproofs ends in the very same conclusion. Let's call that R. Okay, so that is, we have several things. We have the premise P or Q, but we also have the idea that the assumption that P leads to R, and the idea that the assumption that Q leads to R. Right? And so then the logic is, well, I know that either P or Q is true, and no matter which one it is, I know that R is true, because I know that P leads to R, and I know that Q leads to R. And so therefore my conclusion is that R. Because even if I don't know which of P and Q is true, I can still know that R is true, because I know that R is true on the condition that P, and I know that R is true on the condition that Q. The introduction rule for OR is simple, if not immediately intuitive. The idea is that if I have any sentence P, I can just tack on anything I want, P or Q. Okay. Now this is somewhat strange, and it has been troubling to some reformist-minded logicians over the years. We're not going to get into those details here, but suffice it to say that some logicians have been worried about the fact that it seems that Q just appears by magic, and it's a little bit alarming that we can prove a sentence of this shape from a sentence of this shape, because Q just seems to appear out of nowhere, and Q could literally be anything we want. In fact, it could be not P, it could be P, it could be some very long compound sentence, or anything else. But the logic is simple. The idea is that, well, if P is true, then of course it's true that P or Q is true. Because for the disjunction to be true, we only need to be sure that one of these disjuncts is true, and we already know that one of those disjuncts is true. So therefore, in particular, it really doesn't much matter whether Q is true or false. We know that the disjunction P or Q must be true. Moreover, not only do we not need to know whether Q is true or false, we don't even need to know what Q is. Right? And that's this aspect of magic that crops up here. What could Q be? Well, anything. It doesn't matter whether it's true or false, and so in particular, it doesn't really matter what it says. Okay? Similarly, we can start from the right disjunct and conclude the same thing. Okay, and then we have rules for if-then, which is symbolized by an arrow here. The elimination rule is pretty straightforward. If we have the claim that P arrow Q, and in addition we have the claim that P, well then it must be the case that Q is true as well. Because what if P then Q says is that Q is true if P is. And so if we know also that P is, then Q must be true. Okay? The introduction rule is fairly straightforward, a little bit harder to use, but the idea is that, well, if we had some subproof starting with P and ending in Q, then we would be entitled to the conditional claim if P then Q. We're not, of course, entitled to Q, but what we're entitled to is the idea that, well, Q must be true if P is. And that's, of course, exactly what this says, if P then Q. Okay? Let's look at a few examples. These are designed to get the juices flowing, get your minds thinking about how these proofs work. And I'm going to try to, as I go through these, I'm going to try to think about what I'm thinking about in trying to prove these things. Okay. Example 1, prove P or Q and R. Notice the parentheses that mean that this sentence is a disjunction of two things, the sentence P and the compound sentence Q and R. Right? So the parentheses are used for grouping. Prove P or Q and R from P. Okay. Notice here, by the way, that we again have this duplicity of and symbols. Here we have an ampersand, and here we have the wedge shape. This is in part forced upon me by my software program, but rest assured that they mean the same thing. This upside down V and this ampersand both mean and. Okay, well, we're going to set it up in the usual way. We write a vertical bar, and we put P in the first line, because that's our premise here. And we draw a line to indicate that that's all of our premises. Well, sometimes proofs are easier than they look. This one actually follows immediately. This conclusion, P or Q and R, follows immediately from P. All we have to do is use the rule of or introduction. Right? Because or introduction entitles us to stick anything we want next to some sentence that we've already gotten proven. Right? So if we have P, then we're already entitled to P or anything. And in particular, we're entitled to P or Q and R. Okay. Let's go to a little bit more complicated one. Now we're going to prove that if P then R follows from if P or Q then R. Okay. So here's our premise, if P or Q then R. Now our task is to prove this sentence here, P arrow R. Right? Now just think for a moment about how that would go. It looks like we're going to need an arrow introduction, right? A conditional introduction, because that's the shape of our conclusion that we need. And so in order to get that sort of sentence, in order to use the rule of conditional introduction, we're going to have to assume the antecedent here, P, in some sort of subproof, right? And the idea will be, well, let's try to prove R on the assumption that P, because that will set up our use of conditional introduction. And in fact, this is pretty straightforward, because from P, we can then use OR introduction to get P or Q, which I'm doing precisely so as to use this premise that we've got, right? Because if I had P or Q, then I can combine that with P or Q arrow R by using conditional elimination to get R. Okay? And now, lo and behold, I've got a proof of R from P, which entitles me to write down, to end that subproof, and write, well, in that case, P arrow R. Okay? A couple more here. This one asks us to prove the important rule of modus tollens. Modus tollens says that if we have P arrow Q and not Q, then we are entitled to not P. Okay? But this rule admits of proof, given the rules that we've just outlined. And in fact, it's pretty straightforward. The only sort of bit of novelty comes from the insight that we need to assume P. Right? Now, this might sound sort of paradoxical, that we're assuming the very opposite of the thing we're trying to prove. But in fact, proofs like this in logic and in mathematics occur all the time. The idea is just the idea that we had with these rules of negation introduction and negation elimination. So if you look back, right, how do you prove that P? Well, one obvious way to do it is to try to prove a contradiction from the assumption that not P. Okay? Or vice versa, how do you prove that not P? Here's an obvious attempt. Try to prove that the assumption that P leads to this absurdity of the contradiction that Q and not Q. Okay? So that's what we're going to do. So here we are. What we want to do is to prove not P. Here's our conclusion. And so the insight is, well, let's assume that P, and see if we can derive some contradiction from that assumption that P. And in fact, this is readily forthcoming, because if we have P, then from premise 1, we also have Q. That's using conditional elimination. Okay. And that's immediately problematic because we have the premise that not Q. I'm just reiterating that premise here, right? So now we have Q and not Q. There's our contradiction. What was the problematic assumption that led to that contradiction? Well, it was P. Okay? And so the rule of negation introduction now allows us to conclude this subproof and write not P. Okay? And so there we have a proof of not P from these two premises, if P then Q and not Q. Okay, here's one more that's a bit more involved. It asks us to prove the sentence P and Q or P and R, and here it is, from P and Q or R. And here's that premise. Okay. Now, how in the world would this one work? Well, here are the things that are running through my head when I see this. First of all, we start with this conjunction. And so it's probably going to pay dividends to go ahead and use and elimination on this right away. And if we do that, we get the sentences P and Q or R. Right? Now, if we look at the shape of the conclusion that we need, it's an OR statement. And if you think for a moment, you'll be able to see that we're not going to be able to prove either of these disjuncts alone. We cannot prove P and Q, and we cannot prove P and R. Right? Which means that this conclusion will not be proven by OR introduction. Instead, we're going to have to try something else. Now, here's an idea. We have this disjunctive statement here, Q or R. If we could perform an OR elimination on this, we might get what we need. Now, how does OR elimination work? Well, remember, we need two subproofs, one that starts from Q and one that starts from R, and they have to lead to the same conclusion. What conclusion could that be? Well, in fact, we can get this very conclusion that we want. Here's how that works. If we assume that Q, well, then by this previous AND elimination, we know that P and Q is true. And by OR introduction, we can just stick on anything we like to that P and Q. And so since we're interested in P and Q or P and R, we'll add P and R. So here we have P and Q or P and R. And of course, by symmetry of reasoning, we can get that very same result from the assumption that R, this time by conjoining P with R and then adding P and Q to that. And so we end up with the very same sentence in each subproof P and Q or P and R. And now the use of OR elimination comes in, which says that since we have this sentence Q or R, and these two subproofs, each starting from one of these disjuncts and ending in the very same conclusion, we're entitled to that conclusion quite generally, independent of these subproofs. Okay? And once we do that, we've in fact achieved exactly what we set out to prove. We have proven P and Q or P and R from P and Q or R. Okay. More examples to come. That's it for now. Thanks.